now that we've covered scheduling, we're going to go and tackle memory. So memory management, you've heard about paging or not, so we're going to find out. You definitely heard about virtual memory, so we're going to find out what exactly virtual memory is. And we're going to have an overview of virtual machines, because you've heard about virtual machines, hopefully. All right. Whoops, have we seen this before? Yes, definitely you've seen it in the computer architecture or computer organization, it doesn't really matter. This is what we use in an ISA. Remember, we have a place that is for the instructions, a place for static data, dynamic data, and then the stack that we use in functions or in procedures. The heap grows up and the stack grows down. Remember that? You should. So this is for your unit programming system, and this is the how we see the memory from the logical point of view, from the ISA point of view. Okay? Oh, two reserved places. Well, you didn't know why before. Well, today you're knowing why. This one is reserved for the kernel. So this is why you're not allowed to use it when you're assembly programming. You're doing some assembly programming, or you're dealing with the ISA. And this one is actually empty. This small at the very beginning is empty. And if you really want to know why is it empty? Because it's from a historical point of view. So in history, the stack, instead of growing downwards, it used to grow upwards. And remember, back in the days, we didn't have a kernel. So basically, it grows up, and if we have, another process here, so you can notice that if it keeps on growing, it will go to the address space of the other process. So this is why we have a margin here, like a protection margin, even if the stack from the process beneath it keeps on growing, well, at least we're saving it for the first, couple of addresses here. It's not a problem. This is a history anecdote. This is why we have it reserved, and we kept it this way. My question to you is, so this is the memory needs for a process. Where to store the PCB? Whoop, what is a PCB? If someone is asking this question, this means that you don't deserve to be in this course, because we spent so much time in the lectures and in the tutorials talking about the PCB. So the PCB stands for Process Control Block. All right, thank you so much. So who deals with that? It's definitely for the kernel to, keep information about the process. So where do you think we're going to store it? In the reserved place that is used by the kernel. So this is for the whole process, and we have a reserved place for the kernel, and this is where we're going to find the PCB. Now you know why do we have a reserved place for each process. Okay, let's go for the multi-prog memory management. So here's your logical address space per process, and here's your physical memory. What's the difference between logical and physical? Well, physical is the thing that you're gonna, when you open your computer, you're gonna see some RAMs, and these are the RAMs, these are the physical memory. The logical memory, or the logical address space, is whatever is dictated by the ISA. So remember, if we're using 32 bits address space in an ISA, this means that we can go from 0 to the 2 to the power of 32 minus 1, right? So this is our logical address space. What can you notice here? My physical memory is segregated into two spaces. The first one is always dedicated for the OS, so from low to high. And then, have we seen this before? Yes, somewhere, but I'm not going to say where, because you need to remember. And then we have this space that is dedicated for user. So my question is, where in the physical memory we're going to put the user processes? Is it here? If you answer yes, this means that, not good. So it's definitely in the user space, all right? So the whole thing here, for each process, we have here, etc. All right? Remember, processes, concurrent, they fight over the different resources, right? One of the most important resources is the CPU. Another important resource is the memory, the physical one. All right, my question to you is, if I don't have enough space in my physical memory, what should I do? All right, so this is where, and we're going to talk about more details in this lecture, we can swap in and out from the physical memory to the hard disk, to the secondary memory. And swapping maximizes CPU utilization. So why am I doing this animation here? To say that it's extremely important. So here I'm trying to fit as many processes as I can, not fully, but partially, and the other part will be in the secondary memory. All right? Perfect. So memory management requirements. What should we satisfy? So relocation, if I swap out and I swap back in, well, I need to find a new location in my physical memory for the part that I swapped in. The easiest thing to do is what? Is to put it back exactly where it's supposed to be, right? However, is this efficient? Maybe not. So this is why we try to find a new location for that, all right? Sharing. Sometimes processes need to share portions of memory. Why? Because it makes communication easier. So we need to make sure that we're managing sharing correctly. On the other hand, sometimes we don't want to share, and this is true most of the time, right? So we need to protect from unwanted interference. So we need to make sure that process 1 here is not trying to get over the process space, the memory space of the other process, all right? So this is protection. And finally is the, because we have the ISA point of view, so the user point of view, this is what you program, and what really happens physically, so we need the translation mechanism, so from logical to physical. So we can have logical address 1, but physically it could be address 105,000, all right? So we need to deal with the translation. Question is this the responsibility of the OS only? Is it just the OS's responsibility? What do you think? Well, the hardware guys will definitely say, of course not. And this is true. This is why we have in the hardware, physically, in our computer, an MMU, a memory management unit, and something that we call a translation leukocyte buffer. So a translation table in order to be able to get the physical address from the logical address. So this is this is hardware. So hardware plus OS, system software, makes the memory management possible. All right, important part. So focus here. Memory partitioning. So my physical memory, I need to divide it. I need to partition it, have some partitioning of it. I have two options, equal size or unequal size. What do I mean by equal size? So this is low to high. This is my physical memory. I have this part for the OS always. And then I need to get the other parts for the processes. Equal size partitions means that it is the same size for each memory block here, for each partition. So here in this case, it's 8 megabyte, for instance, right? So same size. Unequal size partitions means what? What does it mean? It means that even though it's fixed, I'm not having the same block sizes here. I can have 8, then I can have 4 megabytes, I can have 24, 32, whatever, all right? Which is better? There's no better. It's a matter of a design choice and for different needs, all right? But be careful. If we're using equal size partitions here, this means what? Imagine that my process needs only 4 megabytes of memory. So I'm going to put it in a 8M partition. Why? Because I have no choice. They are all 8. What did I do here? Well, I lost 4 amps. I cannot use because actually the whole space is reserved for my process, but it's only actively using half of it. So this is what we call internal fragmentation. So internal fragmentation means that my process is not occupying fully the whole partition here, And this is why unequal size partitions could help in that. This means that if my process needs 4, well, I'm going to go and put it in the 4 partition here. Should I put it in the 24? No, because I'll be losing 20 amps for nothing. All right? So this is how I place processes. Here I have no choice, so it's easy. Why? Because the very empty one, I'm going to put it in. Here I need to go and look for the best fit. All right? It's always a trade-off between, performance and being optimal, being efficient, etc., etc. This is what engineering is all about. Right, so if I talked about fixed partitioning, what do you think? What am I going to talk about next? Well, dynamic partitioning. Here, well, we're not dividing the memory a priori. We don't have a divided memory at the beginning. Well, we're going to divide it, we're going to use it when the demands are pouring in. So variable length partitions, right? I'm going to find out about that a moment from now. So my OS always occupies the, a particular place of memory. I don't touch that. And I'm going to go check this here. What is the size that I have for my user processes? 56 megabytes. All right, so imagine that process number 1 needs 20. So I'm going to go and put it in the first 20 right after the OS. Make sense? So I'm left with 56 minus 20. I still have 36 here. All right, so process number 2 just arrived and it needs 14. So I'm going to add it right after process number 1, right? And I'm going to take 14. So now I'm left with 22 M. Same thing for process number 3. Now I'm having 18. I'm left with 4 amps. Whoop! Process number 2 is not here anymore. What happened to it? Well, it could be swapped out or finished its execution, so it's not there anymore. All right, it died. All right, so I'm having extra 14 amps free for now. Process number 4 just arrived and it needs 4, so I'm going to put it here in the 14, and I'm left with 6 amps here. Process number 1 is not there anymore, so I'm with 20 extra amps here. And then process number 2 came back, and I gave it this part because this is where I can put it. I don't have any other place for it. What do you notice here? I have a lot of white empty places here. This is a problem, right? Because if I have a 5th process that needs, let's say, that needs 15 amps, for instance, well, I cannot fit it anywhere, correct? So how to deal with that? By the way, this is what we call external fragmentation. The fact that we ended up here, it's called external fragmentation. So what's the solution? Come on, you engineers, you future engineers. What do you think? Yasmin, do you have an idea? So I need to have 15 amps. I have them, but they are distributed. They're not continuous. So what should I do? What do you think? Move up this one, move up that one. Try to compact. This is what we call compaction. So all you have to do is try to bring those closer to each other so I have a big empty white space here. But this is extremely time consuming, okay? Because we need to slide every process upper. So basically, it's time consuming. All right? Yes. So we are always hungry for more memory space. And imagine that you have a little bit, small number of RAMs in your computer, but you need to have the impression of a bigger one. So this is why we're going to use the secondary memory. Swap in and swap out between the main memory and the second memory, and it will give us the impression of one bigger main memory. So the memory management unit is helping us using the secondary memory to have a bigger main memory from the user point of view, from the process point of view. And this is exactly, my friends, what we call the virtual memory. It's not a real one, but it's an impression of a bigger main memory. So virtual memory is equal to main memory plus whatever I'm using in the secondary memory. Pardon. All right. So we said that memory management is hardware and software. So we have the memory management unit and the operating system work together. And you can read that later with the rest. I don't care about that. You can see the picture here. This is what I'm going to explain. From a process point of view, from a user point of view, we have a virtual address. So we can put our stuff in A, B, C, D, and E. All right. So let's say process A comes at 4, here at 0, at 4, at 8, etc., etc. A, B, C, D, and E. A, B, C, D, and E. Right? They come one after the other. However, in the virtual memory, well, they're translated in a different way. So A can go here in this address physically, B can go to that one, and C can go to that one. And because it's virtual memory, so we can use the secondary memory. So basically what we can do here is D and E, we can put them in the secondary memory. And then we can swap them in and out, etc., etc. So this is my virtual memory. All right? So physical memory, physical main memory plus secondary memory. All right? And the fact that we're swapping in and out and distributing in this way, this is what makes it possible to give an impression of a way bigger memory. So see, we can fit more processes here. All right, 2 keywords, pages and segments. So we're going to find out about that. We are going to cover pages in this course, and the segments is good for you to know. All right? So what's a page? So a page is a fixed size logical memory block. All right? So page equal logical memory block, and it's fixed. So if it's fixed, remember from before, if it's fixed, what does it mean? What can we risk? We can risk internal fragmentation. All right? So the program is broken into pages by the memory management system. And then, of course, because we will have translation between the physical and the logical one, we need to maintain a table, for the different pages. So we know that this page will be in the physical memory, and that page will be on the, at the hard disk, or here in the physical memory, or there, etc., etc. So they do not follow the same order from the logical address. All right. So we need to have a translation mechanism. Who takes care of the paging mechanism here? It's not you. It's the OS. It's the system itself, the memory management system, OS and the hardware. All right. Unlike segments, and this is one we're not going to cover here, but I mean this is variable size as opposed to fixed size, and this is the programmer that actually break them into segments. And this is why sometimes when you execute Java or some high-level things, you have some segmentation errors, right? This comes from here. All right. Okay, so let's move to the paging, and this is what we're going to cover here. So follow up, focus here. So the physical and logical memory are divided into the same fixed size blocks, all right? We call them pages in logical memory. This is what I told you before. And in the physical memory, we call them frames. So a page is equal to a frame in the physical memory. All right? Perfect. All right, so here we have an address. And the address is divided into a page number and a page offset. So remember your computer architecture course. Whenever we need To deal with the memory, we need a base and an offset. All right? It's exactly the same thing here. The page number is your base, and the page offset is your offset. All right? So page number is the base address, and the offset is the displacement. It's the displacement. Sorry, it's the offset. All right? This is for a logical address space of 2 to the power of m, and a page size of the 2 to the power of n. And this is the formula how to get it. So to get the page number, it's m from the logical address space minus n from the page size. And then the offset, naturally, it is n. All right? Don't you worry. We're going to have an example right away. All right. Let me explain it a little bit more. All right. So focus. Take a deep breath. Do you think that they need a break? Okay. Give them 5 seconds to breathe. All right. So let's go back to that. Memory management. We have logical address space, and we have physical address space. How big is my logical address space here? It's given. It's 2 to the power of 2, so it's 4. All right? How big is my physical address space? It's given. It's 2 to the power of 3, so it is 8. Okay? You can see here that my page is put at another frame in the physical address. So logically, my page, it's page 0 here, but page 0 is in frame 01 in frame number 2. How big is my page? Well, here in this case, it's 1. Okay? How do I know that page 0 is in frame number 01, 2? Well, I need to find it in the table that is maintained by the OS. So each process table entry has actually the logical address and the physical address. So page 0 corresponds to frame 2, 0, 1, 2. So yes, I'm finding page 0 in frame number 2. All right? What about page 1? So I'm going to go and check it in the page table. So page 1 is in frame 0. So I'm going to go to frame 0, and I'm finding page 1. And you can do the same for the other pages. We good? Perfect. So it is the frame number per the page size, and the page size is here is 1 plus the offset. All right? So page size is 1, I'm having 4 pages here. Page size is 1 here, I'm having 8 pages here, because it's 8 divided by 1, it's 8. Let's see an example. This is what I'm giving you. So consider n is equal to 2 and m is equal to 4. Remember the formula? Logical address space is 2 to the power of m, and page size is 2 to the power of n. This is given as well, 32 bytes of physical memory. All right? So I'm having 32 bytes of physical memory. What is the page size? Page size is 2 to the power of n. So n is equal to 2. So what's my page size? It's 4. We good? So I'm having 4 bytes in each page. We good? Perfect. How many pages can fit in the physical memory? So hold on. If I'm having 4 bytes in a page and I have 32 bytes of physical memory, all I have to do is to do what? Divide 32 by 4. So 32 divided by 4 is 8. So I can go from 0 to 7. This is why I have frame 0 all the way up to frame 7. We good? We good. All right. Now the biggest question is, what is the physical address? And of course, you're going to have this in the exam. Huh? So what is the physical address of logical address 9? How do I do that? Okay. Well, the easiest way is to go here. So let's find logical address 9. It belongs to which table, to which page? Up, 9 is there. So it's J, right? So it's page number 2. How do I know where to find page number 2 in the physical memory? in what frame? Well, I'm going to go to the page table. So page number 2 is in frame number 1. I'm going to go to frame number 1. All right? By the way, what is the offset here? The offset is n, right? So n is equal to what? Yeah. So I'm having 0, 2, it means that I'm having 0 and 1, right? So so I can find my j here. All right? Perfect. So this is paging. Let's go back a little bit to page tables. All right. So we said before that virtual memory, that only some of the process may be in the main memory. Is that correct? Yes, definitely, because the other part is where? Yasmin? If it's not in the main memory, it will be in the secondary memory or the hard disk, all right? So only some of the process may be in the main memory, right? Now the question is how to know actually if it's in the main memory or not. So as engineers, we need to have some kind of information of that, and the easiest way is to have some kind of bit, right? So we're going to say present or not present, so we're going to use a bit, all right? And another thing, well, you know, because memory, it could be some variable or some data, and we can change that data. So how do we know if the content of the corresponding page have been modified? Well, we need to have some kind of bit as well to say that modified or not modified. And by the way, the page tables are where? They're always in memory. Is this a good thing or a bad thing? Performance-wise, it's bad. Why? Because if I need to have some translation of my virtual address, I need 2 physical accesses. The first one is to go to read the table, right? So one to access the table, and the second one is to get the actual thing that I want, the desired element, right? Losing time. If I lose time, you know, from the computer architecture course, if I lose time, it's bad for performance. So think computer architecture, how to make things easier. Well, some kind of cache, right? So basically, to have the information that is ready somewhere. And this is what we call them the translation look-aside buffers. All right? So we have translation look-aside buffers. I'm going to go and check them and then go and get them from the things from the places that I need to get them from. All right? Of course, I need to update the information, and we can have hits and misses. Remember, it's exactly like the computer architecture course. So basically, I need to know how to deal with that and how to, you know, to update my translation look-aside buffer. All right, and this is true as well for the main memory. So if I'm swapping in and out between the main memory and the secondary memory, I need to know, well, do I find it in the main memory or do I need to go and get it from the secondary memory? All right? So we have page replacement policies to know which page to load and to replace it with what page in the main memory. So which page to select in main memory to be replaced. For your info, some frames in main memory, remember a page in the physical memory is called a frame. So some frames are locked. This means that we cannot swap them out. So some of the frames in main memory are locked and we cannot actually be replaced. Like what? What frame or page from a process we cannot put it in the secondary memory? What do you think? Do you have any idea? If you don't, try to think here. Which one do you think that should never leave? One of them. Well, naturally, the one that's going to be used by the kernel. This is minimum, right? So we know how to deal with the process and we keep the things that we need about the process. Where is it? Okay. All right? Now let's see for the others, the one that I can actually swap in and swap out and I can replace. I'm going to teach you 3 basic algorithms because usually in normal times I would ask you to think about the algorithms and propose something to me, but here, because you're not there, you're not here next to me, so you're going to do it at home. I'm going to give you the solution. All right. So we have the optimal, the FIFO, and we have the LRU. Does it ring a bell here? We've seen it somewhere in another course. It's exactly in the CA course. Least recently used. All right, so let's go for the optimal. So optimally, the best solution is to select for replacement the page that is the time to the next reference is the longest. So I'm going to swap out the page that I'm not going to use soon. Make sense? So fewest number of page faults. This means that if I'm going to check a page from main memory, it's not there, we're going to have a page fault. It's like a miss. Okay, this is what we call a miss, a page fault here in this case. So this will minimize the number of page faults. Make sense? Do you think that it's something that we can implement? Definitely not. Why? Because it's the OS needs to have the perfect knowledge of future events. And no one can have perfect knowledge of future events. So OS could know about Corona. So no, it's impossible, right? So this is, and please take notes, this is only and just the standard, a benchmark to compare the real implementation algorithms. All right, this is the optimal. Do they have a practice assignment on that? I think so. I think so, yeah, okay, perfect. So you're gonna have fun practicing that. All right, FIFO. So FIFO is first in, first out. So we're gonna select for replacement the page that has been in memory the longest. So if I use the page, I don't know, 10 minutes ago, so I'm gonna kick it out. It's extremely simple to implement, right? All you have to do is check the timestamp, right? So because we are lazy engineers, so we can implement this easily. However, this is wrong reasoning. Why? Because I might be removing a page that is heavily used, even though that it's loaded a long time ago, but I'm keep on using it over and over and over again. So it doesn't make sense to swap it out, right? So no, I don't like FIFO. It's simple to implement, but I mean, it's wrong reasoning. The best solution is the least recently used. So we're gonna select for replacement that the page that has not been referenced for the longest time. So I didn't use it for 2 hours, so it most probably I'm not gonna use it anymore, right? So how to implement it? Well, usually this is where I ask you to propose to me something, but here you're not going to propose anything. So we're gonna use some kind of tag to say that this shows the last reference, some kind of stamp to say that I used it last time at this particular time, etc., etc. So a little bit more complex implementation, but not that complex. However, the experiments have shown that it works nearly as well as the optimal policy. All right, you're going to have fun with that, practicing it in the, applying it in the practice assignment. I'm done with memories. So memory, logical address, physical address, virtual memory, use the main memory and the hard disk, etc., etc. Now I'm going to go and tackle virtual machines. What can you see here? This looks like Windows 7, and it looks like it's running Windows XP. What? Is that possible? Yes, it is. And here it seems like a Mac OS thing. It looks like it. And it's running Windows 7, it's running even Windows 10. It's running Ubuntu, perhaps. And what is that? Oh, it's another program. All right. So basically, apparently, we could have an OS running an OS. It's like Inception, the movie. Crazy. How come? Well, the answer is virtual machines. So what's a virtual machine? It's an emulation of a computer system. Do you know the difference between emulation and simulation? All right. So an emulation is about the physical characteristics. Simulation is about the rough numbers. You know, it's about software. Emulation is you're trying to reproduce the physical characteristics. Another keyword is the virtual machine monitor, VMM, but I usually, it's also known as hypervisor, and I personally like to use the word hypervisor. So it could be seen as a resource broker, and it sits between the virtual machines, so the things, the incepted operating systems that we, the virtual machines that will run the different operating systems, and the actual physical hardware. So if it's sitting between software and hardware, what should it be called? What type of software is it? Remember? So you remember the layers in a computer? So most probably hypervisors are what? Are they application software? Definitely not, because they're sitting in between things. Are they hardware? Definitely not, because they are in between hardware and virtual machines. So basically, these are system software. All right? So this is what you guys already know. You guys already know the traditional architecture. So I have my hardware here, computer architecture course, the beginning of the OS course. Then I'm having my operating system, including the kernel, and I have applications running over the operating system that is running over the hardware. With virtual machines, I'm having my hardware, then beautifully I have my VMM. What's the other name of the VMM? I just taught you that. It's called a hypervisor, so we're going to use the keyword hypervisor. And then over the hypervisor, I'm having my different virtual computers, virtual machines, all right? So I'm having one OS with the different apps, another OS, so I can have, I don't know, let's say Windows 10 here, right? A hypervisor, let's say, and I can have Windows 10 here, I can have, I don't know, Ubuntu, I can have Windows 7, etc., etc. All right? So hypervisor, it's a resource broker. So it's the one that will distribute the different resources among the virtual machines. Let me ask you a curious question about what class of computers do usually use virtual machines. And this is from your CA course, computer architecture. Remember the different classes of computers? We have desktop computers, personal desktop computers. We had, personal mobile devices. We could have embedded computers and, clusters, and warehouse computers and clusters, and servers, right? So what do you think? Yes, definitely servers. And basically servers, why? Because physically we have like multiple things here, but we're going to try to exploit them to the maximum. So it makes more sense on one machine, on one server, to have different virtual machines for different applications, for different types of users or services, etc., etc. All right? So this is what happens in real life. Servers usually are divided into different virtual servers, so virtual machines. We can protect them. For instance, if one virtual server is attacked, we are saving the physical one because it's divided into many different virtual ones, etc., etc. Okay, so virtualization. It's not an easy word to pronounce. All right, what are the different approaches to that? So having a virtual machine, it's an abstraction. However, if it's an abstraction, we need to configure, the characteristics of a real machine. Let me explain that. When you go buy a computer, right, you're gonna go ask about the RAMs of the computers, of the hard disk that is there, on the operating system that it's running, what if it has a built-in camera, if it has a built-in microphone, what are the different sensors, actuators that attach to it, etc., etc., right? Exactly the same thing when you're building a virtual machine. So first off, and most importantly, you need to specify or to get the number of processors that will be running on your virtual machine. And this is what we call a vCPU. Notice we have a prefix here, V, and V stands naturally for virtual. All right, so virtual CPUs on my computer. I'm trying to build a virtual computer, a virtual machine. Well, I need to specify the number of processors. Question. It's a curious question, and we can have a debate on that. Imagine I'm building a virtual machine using a real machine. I cannot build a virtual machine without a real machine. Imagine my real machine has 4 cores. Can I have more virtual processors, more than 4 virtual processors on my virtual machine if I have 4 physical cores? What do you think? So the easiest answer would be no, because how can I have more processors than 4, because physically I have only 4. The actual answer is yes, we can. So all we have to do is get logical processors out of the physical ones, and then distribute them in the virtual machine. I'm getting tired. All right. But usually you have some systems that will not allow you to go more than the actual physical processors. It depends on the implementation. The amount of RAM that I'll be needing, right? It makes sense. I'm building a computer. Even though it's a virtual one, I'm building a computer. So I need to know how much RAM I'll be using. Question, can I have more virtual RAM than the actual physical one? If someone says no, this means that you didn't understand the previous section of this lecture. Because we just said we can have virtual memory. So basically, yes, we can have more RAM. We can swap in and swap out between the main memory and the secondary memory. All right. So again, for the hard disk, if I want to use network ports in order to be able to use the Ethernet or the Internet or Wi-Fi or whatever. And most importantly, I'm going to specify what is the OS that I'm going to be using on my virtual machine, and the sets of apps that will come to that with that. All right. So these are the questions that I need to ask myself whenever I'm building a physical machine, and it's the same thing when it comes to virtual machines. All right. So let's see, what are the types of hypervisors? Check this out. Let me go back here, for instance. So this is my hypervisor. Remember, it sits between the virtual machines and the what? And the hardware. Make sense? Perfect. So what are the different types of hypervisors that I could have? Easiest thing is bare metal. So native. This is what we call type 1. So native hypervisors. This means that these hypervisors run directly on the hardware. This is what we call them bare metal, because they, figuratively speaking, they touch the metal, they touch the hardware directly. And there's a second type, and this is what we call the hosted hypervisor. So hosted hypervisors, naturally, if this one touches the metal, the second type, it does not touch it, so there's something sitting in between it and the hardware. So it's hosted over an operating system. Okay? So here you're seeing the difference between the two. Bare metal directly related to hardware, right above the hardware here, and hosted, it's hosted on an operating system. So it's crazy. Check this out. So it's operating system over a virtual machine, over a hypervisor, over the real operating system, over the real hardware. So it's kind of fun. And this is why sometimes you, on your own machines, you download and use hypervisors, using your computers. Last thing I want to talk about in this lecture, that was fast. So it's really sad when the students are not here because we cannot, interact. I'm going to talk about para-virtualization, right? Try to say it fast. Para-virtualization, all right? What is that? This is the concept of us letting the guest OS that you're running a virtual machine. Hold on. So if I'm having a guest OS, right, over a virtual machine, this means that I'm using a VMM. Another name for a VMM is hypervisor, right? Why would I do that? First off, why would I do that and how would I do that? Well, if I'm letting the guest OS know that, so I'm going to be using APIs, some way to communicate with the hypervisor, right? So some kind of dictionary, a way to communicate with the hypervisor. What's the goal? What do you think? What do I keep repeating in the CA and the OS course? When it comes to computers, it's all about performance. So we're trying to optimize performance. How? Well, actually, if we know that we're running on a hypervisor, so we need to go and talk to it directly about the resources that I need, etc., that I'll be using. It will help out in the scheduling, etc., etc. Because remember, the hypervisor is the broker between the different virtual machines that are running. So this is the goal in order to do better performance. And this is paravirtualization, is what we call software-assisted virtualization technique. This means that using APIs, so it's software. We good? It's all about performance. So if there's software-assisted virtualization technique, what do you think? What can we have as well? A computer is half software and half hardware. So if you have software here, we'll definitely have some hardware-assisted virtualization. And this is where we have extra instruction sets. Remember in the CA course, right before the pandemic of the corona, in class I told you that we could have an instruction set architecture, so the instructions that are understood by the processor, and we have different types of instructions. So here, when we want to have some hardware-assisted virtualization, we have a special instruction set within the ISA, right, that is dedicated for virtual machines. So the hardware is actually giving you the means to do even better performance. And you can have fun checking online using your favorite search engine, Intel's VMX, or even the virtualization ISA in MIPS. Okay, and that's it for memory and virtual machines. So this is the end of big lecture number 2, and we still have the big lecture number 3, and we're done with the OS course.